At Monday's practice, Lonnie sprints 200 meters, a total of 24 times. At Tuesday's practice, he sprints 240 meters, a total of 20 times. On both days, he rests for 30 seconds between each consecutive pair of sprints. Lonnie sprints at a constant speed of 8 meters per second. On Monday, how many times did Lonnie take the 30-second rest between consecutive pairs of sprints? Well, if she sprints and then rests and sprints and rests like that, right? It goes on and on like this. And eventually sprints, rests, sprints, and then this is her last time. And that's it. You'll notice that the rests are obviously in the middle. Oh, I underlined the wrong one. There's rests. So she will have 24 sprints, but 23 rests, right? Because after the last sprint, there's no rest. I mean, it's done. The workout's over. So 23 is the answer to that question. On Monday, determine Lonnie's total practice time. That is, determine the total number of seconds between the start of his first sprint and the end of his last sprint. Okay, so 200 times 24 is the total time distance of running. So that's 4,800 meters. And then we have 23 rests, and each is 30 seconds long. So that is 690 seconds. Now, what do we want to total number of seconds? So I got to figure out the time for that. Okay. Well, speed is equal to distance over time, or any variation of that formula. So time is equal to distance over speed. So the distance I just got, it was 4,800. The speed, that's where the speed comes in, 8 meters per second. And 4,800 divided by 8, I believe, is 600. So that's seconds. So the total time is the 690 plus the 600. So that's 1,290 seconds. And then part C. Determine how many fewer seconds Tuesday's practice will take compared to Monday's practice. Okay. The first practice was the 240 times 20 was Tuesday, right? So that's Tuesday. And that's 4,800 meters. And then the same thing as here. When we figure out the time, distance over speed, it's the same kind of thing. 4,800 divided by 8, and that's going to be 600 seconds. And then we also have to figure out the rest. Now, it's 20 times, so there's 19 rests, and each of those is 30 seconds. So that's 570. So we got those two guys, and we get 1170. So that's Tuesday's story. And then Monday's story, I think we already did, right? This was Monday. Yeah, so I don't have to calculate it again. So the difference, Monday and Tuesday compared, is what's that, 120? Yeah, 120 seconds is basically the difference between Monday and Tuesday. So that's what's answering the question. Consider the following arrangement of positive integers. The first row includes the odd integer 1. And the second row includes the two even integers, 2 and 4. For k greater than or equal to 2, the kth row begins with the integer that is 1 more than the last integer in the previous row, includes in increasing order k consecutive odd integers where k is odd, includes in increasing order k consecutive even integers where k is even. A useful fact about this arrangement is that the integer in the kth row in the kth position is k squared. For example, 4 squared is 16, and 16 is the integer in the fourth position of the fourth row. So this that they've given you is a huge hint. I mean, if they didn't give that, it would actually make the question challenging. But with it, it's like a giveaway. Because I've seen these questions before, but they didn't give this hint. This hint pretty much tells you how to answer it. So here we go. What is the average of the integers in the fifth row? So let's write this out. Okay, 1, 2, 3, 4, 5. These are the rows. Okay, so some of these they already gave, right? They started you off 2, 4, 5, 7, 9, and then 10, 12, 14, 16. Okay, so how do we make this list, right? Because that's what they gave us. But how do we make the list? Okay, so the list is made as follows. So the first number in the next row will be one more than the guy that was at the end. So one more than 16 is 17. Now, if it's an odd number, you just add odd numbers. And how many is determined by the number of the row. So it's the fifth row, so it'll be 5 numbers. So 17, 19, 21, 23, 25. Okay, let's figure out the sixth row. Sixth row, again, the first number would be one more than the number in the last position of the previous row, so it'd be 26. And then, of course, since that's even, you only put even numbers. And since it's the sixth row, there'll be 6 numbers. So 28, 30, 32, 34, and 36. And then you just keep going like that forever. You got it? Okay, so now they're saying, what is the average of the integers in the fifth row? Well, this is the fifth row. So I'm sure you know how to take the average of those numbers, add them up and divide by 5. And when you do, you'll get 21. I'll let you calculate the average. Which row has the 145th integer in the first position? Okay, so this is one of those questions that takes into consideration this useful fact. And that is a very useful fact because watch, if you just look at the last numbers, right? Even in just this limited kind of list that I made, do you notice what those last numbers are? They're perfect squares. So in the first row, it's 1, and 1 is, of course, 1 squared. In the second row, it's 4, and 4 is, of course, 2 squared. In the third row, it's 9, and 9 is 3 squared. In the fourth row, it's 16, which is 4 squared. This is 5 squared. This is 6 squared, right? Very, very useful if you can figure that out on your own, but they actually gave it to you in the question. So which row has the integer 145 in its first position? So somewhere along the line, you're going to have some row where 145 is the first number, right? So if you go one row before it, the last guy will be 144, right? That's how you go from 144 to 145, according to the rules of the question. Now you tell me, what row will this 144 be in? Well, first of all, what is 144? It's 12 squared. So it would be the 12th row. Basically identical to that pattern. So this was 21, this is 12. Oh, whoa, wait. Let me see if I did this right. No, that's the 12th row, but this is the 13th row. Yeah, because they want, what row has the integer 145? So let me make that a 13. Make sure I do this right. Okay, so I guess I got to read the question carefully. So 13th row. Okay, we got that one. Determine the row in the position in which 1598 appears. So the same sort of story, we got to figure out 1598. Okay, so the first thing I'm going to do is get sort of an estimate, right? I have no idea where 1598 is, but I can kind of approximate it by seeing, because let's say 1598 is here, right? Some row. I don't know what row it is, but some row. Well, the row before it is going to be some perfect square, right? So that will kind of give me a ballpark estimate. So if I take a root of 1598, it's approximately 39.97. So that makes me think that this is the 39th row, and the very last entry of the 39th row will be 39 squared, which is, what is 39 squared? 1521? Yeah, 1521. And then therefore the first number of the 40th row would be 1522. And then you kind of just keep going. And then the last number in the 40th row would be 40 squared. And what is 40 squared? 1600, right? Yeah. So 1598 is indeed in this row. It's actually a little bit further closer. It's actually it's the very second last number. So the answer to this question is 40th row. So 40. Oh, the position also. The position is second last, but I think that's not sufficient. They actually want you to figure out the position. Okay, so this is the first guy. So if you're going from 1522 to 1600, how many numbers is that? 1600 minus 1520 divided by 2. That's 40 numbers. So there's 40 numbers in that row. Well, I don't even need to figure that out. We already knew that in every row, the number of terms equals the row number. Remember, I explained that before. So I really didn't even need to do that. So there's 40 numbers in this row, and it's the second last, so it's the 39th position. All right, so that answers that one. And then finally, the average of the integers in row R is 241. Determine the value of R. Okay, so somehow, somewhere, there's this row R, and the average is 241. So all these numbers, if you add them up, is 241. So if the average is 241, then that means that something that's around 241 exists in that row. So the same kind of story, let me just see what is 241 the square root. It's like a 15.5. So that means the row before it, so the R minus 1 row, that row most likely has the final number 15 squared, which is 225. And therefore this first number would be 226. Yeah. And then the final number in the rth row would be 16 squared, which I believe is 256, right? Yeah. So then I'm assuming that you add up all these guys and divide by R, and that would give you 241. Yeah. And also, we know what R is. R, since this is 16 squared, R is 16. So, yeah, you would add up all these numbers. So 226, 228, 230, all the way to to 252, 254. And then when you add up all these numbers, and then divide by 16, and it will give you 241. So, pretty confident that it's the 16th row. A positive integer is divisible by 3 exactly when the sum of its digits is divisible by 3. A positive integer is divisible by 4 exactly when the positive integer formed by its last two digits is divisible by 4. For example, 3816 is divisible by 3 since 3816 is 18 and 18 is divisible by 3. 3817 is not divisible by 3 since the sum of its digits is not divisible by 3. 3816 is divisible by 4 since 16 is divisible by 4. 3817 is not because 17 is not. Each of the parts A, B, C are non-zero digits from 1 through 9, not necessarily distinct. The 5-digit positive integer 4b5 b2 is divisible by 3. What are the possible values of the non-zero digit b? Okay, so we have 4b5 b2, and they're saying it's divisible by 3. So first you got to add them up. So 4 plus b plus 5 plus b plus 2, and that's going to be 11 plus 2b. And they're saying this is divisible by 3. So if it's divisible by 3, then it's got to be a multiple of 3. So what are multiples of 3? Greater than 11, obviously. 12, 15, 18, 21, and so on. And what's the largest? If b was 9, this would be 18 plus 11. So 29 is about as high as can go, I think. Or can I go higher than that? 18 to 29. Well, yeah, well, let's see here. Yeah, I think 29 is the highest I can go, I'm pretty sure. So 24, 27, and that's it. Because it can never be 30, right? Okay, so let's figure this out. You just do this. 11 plus 2b is 12. That would make b equal to a half. Well, that's no good because b has to be a digit. If it's 15, then that would be b would be 2. 7 over 2 for 18. If this equal 21, it would be 5. 13 over 2 and 8. So the only values for b that are integers are 2, 5, and 8. And I believe that is the answer to that part. The 5-digit positive integer ABA is divisible by 4 and not divisible by 3. Determine the number of different pairs of non-zero digits A and B that are possible. All right. Okay, so I've got ABA, and it is divisible by 4. Okay, so that's the first criteria. But not divisible by 3. Okay, all right. So the first guy basically tells me that this BA is, whatever this BA is, it's divisible by 4. Okay, so I got to make a list here. Hopefully it won't be too long. So I've got my BA, right? Then I have a B and then an A, and then I've got to eventually figure out the sum. If it's not divisible by 3, then that means the sum is not divisible by 3. So the sum would be 3A plus 2B, right? And that cannot be a multiple of 3. So it cannot be 3 or 6 or 9 or 12, ... You guys get the point. Okay, so, and then let's put 3A plus 2B. So I don't think this should take too long. A little time consuming, but it shouldn't be so bad. First of all, let me immediately just put in the numbers that BA could be. Now it's got to be divisible by 4, right? And it has to be at least 12 because these are non-zero digits. So it can't be 4 because I can't put 0, 4. I can't put 0, 8. So 12, 16, and so on. And those are the numbers that are divisible by 4. And of course, I omitted anything that has a 0 in it because B and A are non-zero digits. And then, of course, A and B are just what are the individual digits. So let's fill those out, right? And then we now need to figure out the 3A plus 2B. So the first one, you crunch out the numbers, it'll be 8. The next one would be 20. Next one would be 16, and so on. So let's fill those out. Okay, so now what we can do is we can now eliminate the ones that disqualify and then keep the ones that qualify. So for the ones that are divisible by 4, everything in this column here qualifies because they're all divisible by 4. But then not everything in this column will qualify because remember, it's not divisible by 3. So the 3A plus 2B cannot be a multiple of 3. So let's eliminate multiples of 3. So we have to eliminate this guy, that 27, this 24, this 36, this 24, and that 36. Let me just double check if that is, yeah, I think so. So the only ones we're keeping are the ones I didn't cross out. So if we were to make a list of my ABs, which ones am I keeping here? Oh, I reversed it. Huh. That's okay. It doesn't make a difference. So 2, 1, 6, 1, 4, 2, 8, 2, right? And then what else qualifies? 4, 4, 8, 4, 2, 5, 6, 5. And then the last ones are 2, 7, 6, 7, 4, 8, and 8, 8. So these are the ones that qualify, and I believe that's 12. So 12 is the answer to this question. Part C, a positive integer t is equal to the product of the 4-digit positive integers ACA2 and this 3-digit positive integer BAC. T is divisible by 15, not divisible by 12. Determine the number of different triples of ABC that are possible. Okay, so T is this product. We got AC A2, and then multiplied by this BAC. And it's divisible by 15. So if it's divisible by 15, it's divisible by 3 and 5. There we go. And then what's the other part? The but not divisible by 12. So not divisible by 12. So that means it's not that means it's not divisible by 3 or 4, but it is divisible by 3, so I guess it's not divisible by just 4. That is the conclusion we come to. Yeah. So okay, I got it. Okay, so let's move forward with this. Let's start with the first piece of information that is divisible by 3 and by 5. Okay. If it's divisible by 5, then that means that the last digit must be either 0 or 5, right? Anything that's divisible by 5, last digit is a 0 or 5. Right? Yeah. So we're taking this number and multiplying it by this number, right? So this actually has a 2 already. And BAC are non-zero, right? Is this a continuation? Yeah, A, B, C are non-zero. Okay, so C cannot be a 0. Okay, because I was about to say, well, C could be 0. But no, it's non-zero. So the only thing that C can be, you're going to have to multiply 2 by C to get a 0 or a 5. So, I think 5. You can't get a 5 because 2 times something will not equal 5. But 2 times something could give you a 0. 2 times 5. Yeah. Okay, so the last digit of this whole T's last digit would therefore be a 0. Okay, that's some progress. Now where do we want to go next? We took care of this guy here. Now let's take care of this guy, which is divisible by 3. If it's divisible by 3, then that means either this is divisible by 3 or that's divisible by 3. So that means either ACA2 is divisible by 3 or this BAC is divisible by 3 or both. But this, yeah, or both. But let's just take it one step at a time here. Where do I want to go here? Well, if they're divisible by 3, that means the sum of the digits are divisible by 3. So this would be 2A plus C, which is 5, plus 2. So 2A plus 7 is divisible by 3. Or BAC is divisible by 3. So that means B plus A plus 5 is divisible by 3. Okay. All right, so some progress, but let's see where we can go now. Now I think we have to concentrate on this guy here. Yeah. Where it's not divisible by 4. So because T is not divisible by 12, that means it's not divisible by either 3 or 4, but it is divisible by 3 from the previous piece of information. So that means by process of elimination, it's not divisible by 4. So that means our next point is that AC, what does it mean? If it's not divisible by 4, okay, it means either that ACA2 is not divisible by 4, or it means that BAC is not divisible by 4. Yeah. I think it's and. No, I think I'm going to stay with the or. I think that should be okay. All right, so first let's concentrate on this guy. A2 is not divisible by 4, right? So according to our definition, A2, whatever number that is not a multiple of 4. So it can't be 4 or 8 or 12 or 16, ... all the way up to, what's the largest one? 96, right? So, but you can't have 4 and 8 because that would mean it would be 0 for A. So the ones are 12, 22, 32, 42, 52, 62, 72, 82, 92. And of these, the ones that are not multiples of 4 are 22, 42, 62, and 82. So that means A is either 2, 4, 6, or 8. Okay. So we got this. And if that part, ACA2, is not divisible by 4, we satisfied this criteria. But then we have to maintain this criteria here. At least that criteria. Yeah. So because we got that criteria by making C equals 5. So this is the only criteria left. So that means that this guy, we have to make it divisible by 3. Yeah. And let me just double check. I'm pretty sure. Yeah. 2. Yeah. Okay. So this is going to require a little bit of work. We're going to have to make a table here. All right, let's make a table. Let's see, where do I go? We're going to have to eventually get triples, the number of triples. So we have A, B, and C. And then we're going to eventually figure out B. And then we're going to have BAC. But then, of course, we have to get the sum of the digits. B plus A plus C. And then the value for A. And then for ACA2, it's the sum of the digits. So that's 2A plus 7, right? Because C was established as being 5. And then we're going to see if it's divisible by 3. I think that should cover it. And I'll walk you through this, of course. Okay, let's see what we got. So the A's we have as 2, 4, 6, and 8. Okay, that takes care of that. And this 2A plus 7, therefore, would be 11, 15, 19, and 23. Now, are any of these divisible by 3? No, yes, no, and no. Okay. All right, that's just an FYI. And then now let's turn our attention to this guy. For A equals 2, C is 5, by the way. So this is going to be B plus 7. This will be B plus 9, right? This will be B plus 11, and this will be B plus 13. And so let's take this one step at a time. So now this B plus 7 has to be divisible by 3 in order for this criteria to hold true. So that means B would have to be either 2, 5, or 8. Got it? That would make the B plus 7 equal to either 9, 12, or 15. So the number of values for A, we have 1, just as 2. The number of values for B, we got 3. And the number of values for C is just 1. So the number of triples, it looks to me, is 3. You got it? Okay, so the next one, same kind of story here. Well, here's the thing here. This guy is divisible by 3. So it doesn't matter what BAC is. B could be anything. Yeah, because we've already satisfied the criteria with this guy. Yeah, it's... Yeah, so that means that this B could be anything. So that means we have 9 possible values for B. Anything from 1 to 9. And therefore, this is always just 1, this is 1, this is 9. So we have 9 triples there. For the next one, same kind of story. B would be equal to either 1, 4, or 7, I believe. So we got 3, 1, and 1. That's 3 triples. And the last one, B, I believe, is 2, 5, and 8. So again, we got 3, 1, and 1. Those 3 triples. And when you add these all up, you get 18. And that completes the question. A lab has 50 computers, numbered 1 through 50. Each pair of computers is connected to each other by a cord. The cords are colored according to the following rules. If the numbers of the two computers are both even or both odd, then the cord connecting them is red. Otherwise, the cord is blue. A route is a sequence of cords along which data can travel to get from one computer to another. With the lab, for example, data could travel from route 5 to 12 or from 5 to 15 to 12. There is a route connecting computer 1 to computer n using only red cords. If n is not 1, how many possible values are there for n? Okay, so you could have a computer, let's say, so you have computer 1, and it connects to some computer. And what color is it? Only red. So red is happening if they're both the same parity, right? If they're both even or if they're both odd. So since one is odd, this one has to be odd also. So just put odd in here. And how many odd numbers are there? All the numbers from 3 to 49, because the numbers go from 1 to 50, right? The computers are labeled 1 through 50, so the odd numbers are obviously 1, 3, 5, all the way up to 49. And that is 3 to 49 is a total of 24 numbers. So it looks like the answer is 24, but then you could keep going here, right? You could have 1 connected to some odd number, odd, and then that's connected to another odd number. So for example, if this was 5 and this was 17. Now there's 24 choices here, but 23 choices here. So using only red cards for n. So this now is 23. So I think the maximum value is 24, because with each scenario, the numbers just keep getting smaller. So the maximum looks like 24, and I think that's the answer to the question. Show that for every pair of distinct computers, computer A and computer B, there's always a route between them that uses only blue cords. Okay, so first of all, we have computer A and computer B. Now, if this is even and this is odd, meaning they have different parity, then the connection between them would be blue, right? Yeah, different parity, it's blue. Okay. And then if you have the same parity, so for example, if this was odd and this was, well, we're not interested really in red. I'm just going to concentrate on blue. So odd and even, that would also be blue. Yeah, don't worry about the red for now. Now let's talk about the red once we've established this part. Then what they're saying is, they want you to show that you can always connect them with blue somehow. Okay, so let's say we have A and B. Well, these scenarios, if they are different parity, then you can always do it. But what if they have the same parity? Let's say A and B were both even. Or, yeah, even. So this is even, and this is even. Well, since it's the same parity, it would be red, right? Yeah. So that means this guy would have a red. But you can always find an even number. So, or sorry, an odd number. Let's say put an odd number in here. And therefore, between the even and the odd, it would be connected by a blue. And between that odd and the even, it would be connected by blue. So that scenario shows that you can always connect computer A to computer B by blue cords if you follow this route, even if they are even and even, through another intermediary computer that is labeled with an odd number. And then our final scenario would be, was odd and odd, So I have A and B again, and they're odd and odd. And since they're the same parity, they're connected to each other with red. But you can always find a computer that is even, and therefore it would be connected to the odd with a blue and connected to the other odd with a blue. So there you go. Again, A and B could be connected in a route via this even number with blue chords. Each red chord and blue chord is removed and randomly replaced with either a green chord or a yellow chord. Danny notices that there is no route that connects computer 1 to computer 50 that uses only green chords. Show that there is always a route between computer 13 and 14 that uses only yellow chords. So there's no route of only green chords. So if you have computer 1 and computer 50, right? There is no route of only green chords. So that means if there's a chord between them, it's got to be the other color, which in our case is only yellow. Yellow is the only color we have. So let's just put a yellow chord there. Yeah. Okay. And then they're saying they've got another scenario where you want to connect, you got to have 13 in there somewhere, or 14 in there. So you got 1 to 13, and then 13 to 50. And then you've got another scenario, you have 1 to 14, and 14 to 50. Like that. Okay. And our colors are only green and yellow, right? Green and yellow are our only colors here. Green and yellow. So computer 1 to computer 50, there's no route that uses only green chords. So that's got to be yellow there. And similarly, even if you put an intermediary in there, like this 13, it's got to be, there can't be both green. They can't be both green. So one of these has to be yellow. So either this has to be yellow or that has to be yellow. So this has to be yellow or that has to be yellow. Yeah. Because they both can't be green, since there is no route that connects 1 to 50 using only green chords. Okay, I got it. And very similar to the 14, even if you put an intermediary in there, same story. There is no route that connects computer 1 to computer 50 that uses only green chords. So at least one of them has to be yellow, like that. They both can't be green. Okay, so I think I got it. All right, so now that makes me have 4 scenarios, right? This is scenario 1, let's say. This is scenario 2. This is scenario 3. And this is scenario 4. So scenario 1 is that the chord between 1 and 13 is yellow. Scenario 2 is the chord between 13 and 50 is yellow. Scenario 3 is the chord between 1 and 14 is yellow. And finally, scenario 4 is the chord between 14 and 50 is yellow. All right. So now let's make those 4 scenarios, and let's see if this helps us solve the question, yes or no. Okay, so the first scenario is 1 and 3. Yeah. The next one would be 1 and 4. The next one is 2 and 3. And the last one is 2 and 4. Okay, so now let's make the diagrams. So we have 1, 13, 14, and 50. So the chord between 1 and 13 is yellow. So 1 and 13 is yellow, so that guy, right? Yeah. And then 3 means the chord between 1 and 14 is yellow, so this guy. And the chord between 1 and 50, according to this guy up top, we had established that it has to be yellow. because it cannot be green according to the definition of the question. So that's yellow. So what does that prove? Show that there is always a route between computer 13 and 14 that uses only yellow chords. Well, yeah. From here to there. That route right there. 13 to 1, 1 to 14, or 14 to 1, and 1 to 13. You got it? Hopefully that makes sense. Okay, so let's do the same thing. Let's see that if it holds true with this guy. Okay, so we got 1, 13, 14, and 50. Okay, so this is a 1 in 4 scenario. So 1 is basically means that this guy right here between 1 and 13. So 1 and 13 is yellow, and then 4 is this guy right here between 14 and 50 is yellow, and then we know from this over here that between 1 and 50 is yellow. So yeah, there's a connection between 13 and 14 using only yellow chords. You go 13 to 1, 1 to 50, 1 to 14, or you can go the other way backwards. And similarly, you guys can figure out the other two. I'll just do them really quick. 1, 13, 14, 50. So this one is 2 and 3. So 2 was 13 and 50, right? So that's yellow. And then 3 was 1 and 14, so that's yellow. And then we know that's yellow. So again, we can go from 14 to 13 using yellow chords only. And finally, 1, 13, 14, and 50. So this is 2 and 4 this time. So 2 was between 13 and 50. Yeah, 13 and 50. And then 4 was between 14 and 50. And there you go. Just that connection right there shows you can go from 13 to 14 with yellow chords. And that completes the question.